this video, we're going to talk about the ketone body's metabolism. So we're going to discuss both the anabolism and the catabolism of ketone bodies. We're also going to discuss the situations when we synthesize ketone bodies or when we degrade ketone bodies. So why do we need to synthesize ketone bodies? You know, ketone bodies can be used as a secondary source of energy or supplementary source of energy during certain conditions of the body. You know, the primary source of energy for the body is the carbohydrate, the glucose. But now, in certain conditions, for example, the starvation, we're going to have the metabolism of ketone bodies. Ketone bodies are very much crucial because they provide energy for the brain, the muscles, the heart, you know. Yeah, so that's the reason why we need ketone bodies. But at the same time, the oversynthesis of ketone bodies is very much dangerous because it's going to cause something called ketoacidosis. That's the increased hydrogen ions in the bloodstream, and that's very dangerous. So we're going to discuss everything in this video. So let us start. When we synthesize ketone bodies, just as I said, the primary source of energy is glucose. Now, we synthesize ketone bodies when number one, there's low blood glucose level. So, low blood glucose. We're going to synthesize ketone bodies. Number two, we're going to synthesize ketone bodies during starvation, during conditions of starvation. Alright. Number three, we can also synthesize ketone bodies, for example, in patients with diabetes mellitus. You know, those people who are diabetic, especially diabetic mellitus type 1, right? When there's insulin deficiency, we're going to synthesize ketone bodies. So diabetes mellitus. Another condition in which we can synthesize ketone bodies, you know, during starvation, yeah, when you starve, of course, you know there's low blood glucose level, right? So during starvation, you are going to have low blood glucose level. But now in conditions when you are eating ketogenic diet, maybe you are trying to avoid eating carbohydrates, so that you can just call Atkins diet or ketogenic diet. So Atkins diet. So when you avoid eating carbohydrates, you know, you're going to reduce the amount of glucose in the body. So let us see the primary source of energy and what is going to happen. Now, for example, in your liver, you're going to have glucose, right? You're going to have glucose. Glucose will always be broken down by glycolysis. So you can break down glucose by glycolysis. You're going to form pyruvate. Then pyruvate can be converted into acetyl-CoA. Acetyl-CoA, right? To the pyruvate dehydrogenase complex. Now, acetyl-CoA can then react with oxaloacetate. They can react with oxaloacetate from citrate. Then you are going to run the TCA. You know the citrate, isocitrate, alpha-ketoglutarate, the fumarate, oxacinyl-CoA, fumarate, malate, and everything of the TCA. Right. Then you know from the TCA you always generate the NADHs, the FADH2, and a small amount of energy through substrate level phosphorylation. So also going to generate some energy, a small amount. Then you know when we take the NADHs and FADH2, we are going to take them to the electron transport chain. To the electron transport chain, we are going to generate energy in the form of ATP. So we are going to generate energy. ATP. That is always the pathway. But now in this condition where we have low blood glucose level, to mean the blood glucose level is low. That is to say that we don't have glucose to break through the glycolytic pathway. So acetyl-CoA will be low, then you are going to have low, then low ATP. Now, what will happen when you have low ATP? You know, we need the energy for muscle contraction, for digestion, for everything. So we need energy so much that we cannot afford life without energy. And therefore, what the body is going to do is going to divert into another pathway. Let us see what's going to happen. The body is going to divert into breakdown of fatty acids. Now, when you have fatty acids can be broken down into acetyl-CoA. And you know this process? This process is called beta oxidation. The process by which we break down fatty acids into acetyl-CoA. Now, when we break down fatty acids into acetyl-CoA, you are going to run the TCA, then you are going to revive the energy supply for the body, right? But now, the body is going to undergo a process called gluconeogenesis. The body is trying to convert oxaloacetate back to bring back glucose level back to normal, you know? Yeah. So what's going to happen here? As we are running the TCA, generating NADH, FADH2, ATP generation, some amount of oxaloacetate is going to be converted into malate. So here we have malate. This reaction here is reversible because oxaloacetate cannot penetrate the mitochondrial membrane. Suppose this is our mitochondria. Oxaloacetate cannot penetrate the mitochondrial membrane. So what is going to happen is going to convert into malate, then malate is going to penetrate, then be converted back into oxaloacetate. Oxaloacetate can then be acted upon by an enzyme, and this enzyme, you know the name of this enzyme? This enzyme is called PepsiK. So, PepsiK. PepsiK simply means phosphoenol pyruvate carboxykinase. Phosphoenol pyruvate carboxykinase is going to convert oxaloacetate into PEP, or phosphoenol pyruvate. Then you are going to run all the way through gluconeogenesis pathway. I hope you know that. Then you are going to form glucose. So we are going to try to revive the glucose level in blood. Now, when you have taken oxaloacetate to malate through the gluconeogenesis pathway, to mean you are going to have less oxaloacetate to interact with the acetyl-CoA so that you can learn the TCA. So that is to say that you are going to have accumulation of acetyl-CoA because you don't have the oxaloacetate to interact with it so that you can form citrate and everything in the TCA. Now, that is going to have accumulated amount of acetyl-CoA in the cytosol. So what is going to happen? We are going to react the acetyl-CoA is going to react with each other. Then what are you going to form? When we react with acetyl-CoA and another acetyl-CoA, we are going to form a new molecule. This new molecule is going to be called acetoacetyl-CoA. It's going to be called acetoacetyl-CoA. Alright, what is going to happen? We only have one CoA here. So we are going to lose it. We are going to lose a CoA. Alright, now, what is the name of the enzyme that catalyzes this reaction that fuses the acetyl-CoA and another acetyl-CoA? Now, this enzyme is going to be called thiolase, or the other books you can find it called acyl-CoA acetyltransferase. But I'm just going to make it simpler. I'm just going to call it thiolase, or acyl-CoA acetyltransferase. Alright. Then acetoacetyl-CoA is going to be converted into a new molecule. Now this new molecule is going to be called HMG-CoA. Now this is just the abbreviation. It's called beta-hydroxy beta-methyl glutarate-CoA, or 3-methyl-3-hydroxy 3-methyl glutarate-CoA. So that's the full name for HMG-CoA. Now, this reaction is going to involve input of acetyl-CoA. So I'm going to input acetyl-CoA, then I'm going to get rid of the CoA. Alright, now what is the name of the enzyme that catalyzes this reaction? This reaction is catalyzed by an enzyme called HMG-CoA synthase. So, HMG-CoA synthase. And this HMG-CoA synthase is a very enzyme because it is the rate limiting step in this particular pathway. So it is a very, very much important enzyme. Now, we have our HMG-CoA synthase. HMG-CoA is going to be converted into a new molecule. Now, actually, we are going to involve a cleavage. So, HMG can be cleaved into a molecule called acetoacetate. So acetate. Right. Now, do you know this? This is already a ketone body. Acetate is a ketone body. So let me just write here, ketone body. Ketone body. This is our first ketone body, the primary ketone body. Now, what is the name of the enzyme? What happens in this reaction? In this reaction, you are going to lose acetyl-CoA. Alright, then what is the name of the enzyme that catalyzes this reaction? This reaction is catalyzed by an enzyme called HMG-CoA. So, HMG-CoA is going to lyse. You see, lyses. Alright, now we have acetoacetate. It's already a ketone body. So it is from the acetoacetate that we are going to generate other ketone bodies. Now let us see what's going to happen. First of all, this acetoacetate can be released into the bloodstream. Portion of it can be released into the bloodstream. Then some can also be converted into a new molecule. Now see this. Acetoacetate can be converted in a molecule called beta hydroxybutyrate. So you have beta hydroxybutyrate. Beta hydroxybutyrate is also a ketone body. Is also a ketone body. Alright, then how do you form beta hydroxybutyrate? Forming beta hydroxybutyrate, we are going to involve NADH, right? So we are going to have the NADH is going to unload the hydride, then it's going to be converted into NAD+. It's going to be oxidized, while we are going to reduce the acetoacetate into beta hydroxybutyrate. Now, there's another ketone body. We can convert acetoacetate into another molecule. Now see this. Acetoacetate can be converted into a new molecule. Now this new molecule is going to be called acetone. So, acetone. Now acetone is another ketone body. So, this is a ketone body. Now, what is the name of the enzyme that catalyzes the formation of beta hydroxybutyrate from the acetoacetate? When I told you that whenever you see the NADH, the FADH2, to mean the enzyme is a dehydrogenase. So this enzyme is going to be called beta hydroxybutyrate dehydrogenase. So beta hydroxybutyrate dehydrogenase. So that's the enzyme that is going to catalyze that reaction. Alright. Then acetoacetate into acetone is going to be converted by an enzyme, and this reaction is going to involve the loss of carbon in form of CO2. Alright. Now, this enzyme that catalyzes this reaction is going to be called acetoacetate decarboxylase. Acetoacetate decarboxylase. So I'm going to have acetoacetate decarboxylase. Alright. Now, these ketone bodies, you have the acetoacetate, you have the beta hydroxybutyrate, then you have the acetone. They can be released into the bloodstream. And also, the acetone can also be released into the bloodstream. So that we are going to have elevated levels of these ketone bodies in our bloodstream. Now, what is going to happen? You know, the beta hydroxybutyrate and the acetoacetate, they have a pKa. Let me tell you this. They have a pKa of about 4 to 5. Right? So when they have a pKa of about 4 to 5, to mean they are acidic. So, acidic. That is to say that when they get into the bloodstream, they are going to donate protons. So, we are going to have protons in the bloodstream. Elevated amount of protons in our bloodstream. That is to say that blood is going to become acidic. So the blood is going to become acidic. Now, How do you call this condition? When the blood is acidic. This is called acidosis. But now, because it is brought about as a result of the donation from the ketone body, specifically, it's going to be called ketoacidosis. So you can call this ketoacidosis. Ketoacidosis. Now, ketoacidosis is characterized by acidic blood. Now, this is very much dangerous and can lead to comatose. Can lead to a condition called comatose. And sometimes can even lead to death because it is very much dangerous. Now, another condition we said, forgot to mention this, acetoacetate is converted into acetone. Now, acetone is always released in breath, and that is can be used as one of the diagnostic markers for patients with diabetes mellitus type 1. Forgot to mention this. Diabetes mellitus specifically type 1. Now we can smell the breath of these patients. Then when we feel or when we sense the acetone breath, then we can say that they are indeed having ketoacidosis besides diabetes mellitus. Right. So we are going to have acetone breath. Acetone breath. Alright. Then there's also what's going to happen. The acetoacetate can move to the part of our brain. You know, there's a section of our brain called postrema. The postrema, right? There's a section of the brainstem called postrema. Just right here. Postrema. This is where you have the chemotrigoson. The chemotrigoson is found there. So what this postrema is going to do when the acetoacetate moves to the postrema and activates it, this postrema is going to activate or is going to induce vomiting. So these patients are also going to have vomiting. Alright. What is vomiting going to bring? When you vomit, you know you lose a lot of water, a lot of electrolytes, everything. Then so this is going to lead to another condition called hypovolemia. Hypovolemia simply means low blood volume because you've lost a lot of fluids in our body, so there's low blood volume. When there's low blood volume, this can also lead to a condition called, we're going to reduce the blood pressure. The blood pressure is going to reduce, right? Alright, we're going to reduce the blood pressure. Now, this is also very much dangerous because it can lead to a condition called, this one can also lead to comatose. Alright. Now, what is going to happen? When you have a lot of ketone bodies in our blood, the beta hydroxyurea as a acetate, adequate amount in our blood or more than enough amount in our blood, some can be transported to the kidney so that they can be released in the urine. So this is going to be called a condition, it's going to be called ketonuria. Of course, we always know that we should not find ketone bodies in our urine. But now in this case, the body is going to try to eliminate some of these ketone bodies via the urine. Now, the body will try to adjust to this particular condition when you have a lot of acidic blood, right? Now, so the solution that the body is going to find is that we are going to increase our breath. We are going to breathe very deeply. You see, we are trying to get rid of the carbonic acid, the protons, and everything, the carbon dioxide in our blood. So that is the solution. And the body is going to try to find so as to get rid of the protons in our blood and everything, right? And this condition is going to be called, so you can say solution is going to be called Kussmaul breathing. When there is increased breathing or elevated level of breathing or hyperventilation. You're breathing very rapidly so that you can get rid of these protons, the CO2, and everything. Now, let us see what's going to happen to our beta hydroxyurea and the acetoacetate. Alright, because you know, it's only the excess amount that is very dangerous, but also they can be useful because we can use them to generate some energy for the brain, for the muscles, for the heart. Now, let us see what's going to happen. The beta hydroxyurea, we have our beta beta hydroxy butyrate. Then we have our acetoacetate. This is in the muscle, right? Because I said we can transport these onto the muscle, skeletal muscle, for example. So, that means very well. So, inside our muscle, the beta hydroxybutyrate is going to be converted back into acetoacetate. Now, let us see what's going to happen. Remember, while we were forming the beta hydroxybutyrate from acetoacetate, we used NADH. Now, in this case, we are going to convert the NAD blood is going to be converted to NADH. That is to say that they are going to be reduced. So, it means you are going to oxidize beta hydroxybutyrate into acetoacetate. This reaction is reversible, right? Now, this reaction is going to be catalyzed by the very same enzyme, and this enzyme is going to be called beta hydroxybutyrate dehydrogenase. So, beta hydroxybutyrate dehydrogenase. So that enzyme is going to catalyze that particular reaction. Now, acetoacetate can be converted into a new molecule. So acetoacetate can be converted into acetoacetyl-CoA. So I want to have acetoacetyl-CoA. We will bypass the HMG-CoA. So what is going to happen? Remember the acetyl-CoA, the TCA? Acetyl-CoA, you have to go to the last stage, and we went through the TCA, and there's a molecule here called succinyl-CoA. You have the succinyl-CoA. Succinyl-CoA is going to be used. Let me use a different pen. Succinyl-CoA is going to be brought here. Then it's going to release the CoA. Then you're going to form succinate. Alright. Now, when we unload the CoA into acetoacetate, it's going to be converted into acetoacetyl-CoA. Now, the enzyme that catalyzes this reaction is going to be called thiophorase. Thiophorase enzyme. Thiophorase is going to catalyze that particular reaction. Now, we have our acetoacetyl-CoA. You know what made up the acetoacetyl-CoA? We have the acetyl-CoA. So we are going to break or cleave the acetoacetyl-CoA into two molecules of acetyl-CoA. So we have acetyl-CoA and another acetyl-CoA. Alright, now what is going to happen? We are going to introduce an we're going to introduce a coenzyme A. Now the name of the enzyme that's going to catalyze this reaction is thiophorase, called acyl-CoA acetyltransferase. So I'm just going to say thiophorase. Thiolase, not thiophorase. Thiolase enzyme. Or some books say acyl-CoA acetyltransferase. Now, where can you take the acetyl-CoA? Remember this? You can take this into the TCA, right? You can take this into the TCA. So, you can react this acetyl-CoA with acetate. Then I'm going to form citrate and everything, alpha-ketoglutarate, succinyl-CoA. We're going to have all those other components of the TCA. Then the same this side, we're going to react this one with acetate, then citrate, then everything in the TCA. Alright, now what would we form from the TCA? From the TCA, we form the NADHs, the FADH2, also a small amount of ATP through substrate level phosphorylation. Then the same this side, we will form NADHs, the FADH2s from the TCA. Now, where we take this? We take this to the electron transport chain. So we're going to take this to the electron transport chain. Now from the electron transport chain, you're going to generate what? Now what you're going to generate from the electron transport chain, you're going to generate ATPs. A good amount of ATP. Now, the process by which we synthesize ATP from the electron transport chain is through oxidative phosphorylation. Now, oxidative phosphorylation helps us synthesize a great amount of ATP so that we can run a series of functions in the body, for example, muscle contraction, everything that requires energy in the body. Now, that's for ketone bodies. I think that's true for that. But now, someone may ask, why don't we just use the fatty acids for energy apart from the ketone body? Now, the answer to the question is this. Ketone bodies can penetrate the blood-brain barrier, but the fatty acids cannot penetrate the blood-brain barrier, the BBB. Therefore, there's no way we can break them, we can synthesize, or we can utilize the fatty acid for energy. And that's why ketone bodies are very, very much crucial in terms of energy supply to the brain and muscles and everything. So thank you very much, guys. If you found this video helpful, please subscribe to my YouTube channel, like and comment. Stay tuned for our next video.